All right, let's talk about the universe's ultimate rulebook. We're diving into a branch of science called thermodynamics, and trust me, it's not just some dusty old topic. It literally governs everything, from how stars burn to why the steam is rising from your coffee cup. So let's get right into it.
I mean, you've seen this a million times, right? You make a nice hot cup of coffee, you get distracted, and when you come back, it's lukewarm. Same thing with the cold juice from the fridge. But have you ever noticed it never ever goes the other way? Your cold drink doesn't just start boiling on its own. So, what's up with that?
Well, the answer isn't magic. It's physics. Both that coffee and that juice are just following the rules. There are these powerful invisible laws pushing them to find a balance with the room they're in. And this whole tendency toward balance, it's all laid out in the laws of thermodynamics. So, to really get why our coffee gets cold, we first need to understand the science that's calling the shots. Let's start with the basics. What even is thermodynamics?
At its heart, thermodynamics is really just the science of energy. It's all about how energy moves around, how it changes from one type to another, and this is the really important part, how we can actually harness those changes to do useful stuff, like, say, powering a car or generating electricity.
You know, this whole field really kicked off back in the Industrial Revolution. You had all these brilliant people trying to figure out the best way to take the heat from burning coal and use it to power massive steam engines and factories. That one challenge, turning heat into actual useful work, that's where it all began.
Okay, so before we can jump into the laws themselves, we need to get a couple of key terms down. It all starts with defining what it is we're actually looking at.
So first, we've got to define our area of interest. In thermodynamics, we call this the system. It can be anything, an engine, a chemical reaction, or, yep, that cup of coffee on your desk. Everything else in the entire universe is called the surroundings. Now, a system can be open, like a pot of boiling water just letting steam and heat escape everywhere. It can be closed, kind of like a sealed jar, where only heat can get through. Or it can be isolated. Think of a perfect thermos, where ideally absolutely nothing gets in or out.
All right, with that out of the way, we're ready for our first rule. And funny enough, they call it the Zeroth Law. It's all about finding balance.
Okay, I know, that sounds super formal and a little confusing, but the idea behind it is actually something you already know intuitively. It's just a fancy way of saying if two things are the same temperature as a third thing, then they must be the same temperature as each other.
Let's just break it down with this diagram here. Imagine object C is our thermometer. We stick it in object A and get a reading. Then we take that same thermometer and stick it in object B. And if the reading is exactly the same for both, well, then it means A and B have to be the same temperature. They're in what we call thermal equilibrium, and that is exactly what's happening on your desk. The coffee, which is A, and the juice, which is B, both eventually reach the same temperature as the air in the room, which is C. Once everything matches, the heat stops flowing. That's equilibrium.
Okay, so if the Zeroth Law tells us where energy is headed, towards balance, the first law tells us something fundamental about what energy is. And this is one of the most famous rules in all of physics.
Here it is, the big one. The total amount of energy in a closed system is always constant. You can't just make energy out of nothing, and you can't make it disappear into thin air. It just changes its outfit. This is the incredible law of conservation of energy.
And these transformations are happening all around us, all the time. Just think about a kid on a swing. At the very peak of the arc, up at point A, all that energy is stored up as potential energy. But as the swing swoops down to the bottom, to point B, that potential energy instantly converts into kinetic energy, the energy of motion. No energy was lost, it just changed its form. Or hey, here's another tasty example. When you eat an ice cream cone, you're taking in a bunch of chemical energy locked away in its sugars and fats. Your body is this incredible conversion machine that takes that chemical energy and turns it into other stuff, like the heat that keeps you warm, and the kinetic energy you use to run around. See? The energy isn't gone, it's just been repurposed.
So, we've seen how energy finds its balance and how it's always conserved. But let's zoom out. What's the big picture here? Why are these laws so incredibly important?
So let's wrap up what we've learned. The Zeroth Law, that's the rule of balance. It tells us that energy always wants to spread out and reach equilibrium. The first law, that's the rule of accounting. Energy can change its form, but the total amount never ever changes. These two rules together are like the unseen architects of our entire universe, shaping everything from technology to life itself. And now for the big one. Seriously, the second law is probably the most famous and honestly kind of the most poetic of all the laws. This is the one that explains why time seems to move forward, why things tend to break down, and yes, why our coffee gets cold.
This right here is the law that answers our big question from the beginning. The key word is entropy. Now, people often call it disorder, but a better way to think about it is how spread out energy is. The second law says that in any closed system, energy always tends to spread out, to go from a concentrated state to a more scattered one. That's why the concentrated heat in your coffee naturally spreads out into the cooler room, and never ever the other way around. This constant, irreversible spreading out is what gives time its direction. It's the universe's one-way street.
And that leads us, naturally, to our final law. So if heat is the energy of motion, and that energy is always spreading out, what happens if you try to remove as much of that energy as you possibly can? What is the ultimate state of order? That's what the third law is all about.
The third law says that as you cool something down toward the coldest temperature that can possibly exist, a state we call absolute zero, its entropy gets as low as it can possibly go. In theory, at absolute zero itself, all the little jiggling atoms would just stop, creating a state of perfect order. But, and this is the amazing part, it's a fundamental limit of the universe. We can get unbelievably close, but we can never actually reach it.
And there you have it. From a simple drink matching the temperature of a room, to energy just changing its costume on a swing set, all the way to the unstoppable march of universal disorder and the ultimate unreachable limit of cold, these four laws are the complete rulebook for how energy works.